Material. But why do we care about material? Well, we cannot do a design or manufacture something if we don't know the property of a material. In particular, we need to know for any things that we make, we need to know how strong it is. And you notice I said how strong. So that's a sort of a layman or layman term. When we say strong, we need to say, what do you mean by strong? We talk about the strength, and by strength, we're talking about the yielding strength. About its stiffness, module of elasticity, toughness, how tough the material is, and when the material is under impact, does it crack? Does it absorb energy so it deform and not crack? And when we talk about hardness, how strong it is when it is under, let's say, scratch or indentation. And durability, if you're using it for a long time, or if it is under cyclic load, like a gear or a cam, can it stand the fatigue life? So all these terms, which we refer to them as mechanical properties. So let's call them mechanical properties. Also, we care about the weight of a material, like its density, about its heat and electrical, basically conductivity. And also, it is important for us to see if the material we pick for a particular application, if it is resistant enough to corrosion. These properties, we refer to them as physical properties. Also, we care about the appearance and the feeling. Remember the last time you wanted to buy, let's say, a cell phone, how much time you spent figuring out you want to go with a maybe aluminum-based iPhone or a stainless steel-based iPhone. What color do you want to pick, right? So, and also the feeling. So, you know, when you have a laptop, if the body of the laptop is aluminum, give you a good feeling rather than if it is a plastic feeling. Although the main function of laptop is something else, but still you care about appearance. What else? We need to know how much the raw material costs. And also we need to know how we want to process the material. Do we want to, for example, machine the material and make something? So then it is important for us to pay attention that it is machinable, or we can cut it. For example, you may go with a very hard and very strong material, such as tungsten, but you cannot machine it. If, for example, you decide to do it by casting, so then it is important for you to know the melting point of the material. If you go with a material which its melting point is high, then it's going to be very, very expensive for you if you pick that material. And many other things that you need to consider. For example, if you decide to make something by forming. So again, it is important to know how brittle or ductile is the material, how flexible it is so you can form it. And also you need to care about safety. You may say, why safety? Well, there are certain materials that maybe some people are all allergic to, which you also must pay attention to that concern as well. All of these things, we call them the manufacturing properties. So combination of all of them, we call them manufacturing properties. So manufacturing properties. And beside these, you may also consider the ratio between these things. What do I mean by that? A material may be very, very strong, so you are happy with that, but for a certain application, it is heavy. So in that sense, you need to also look at the strength over its weight, or this ratio. In other words, you need to look at SY over density, which is called specific strength. Similarly, you need to look at the stiffness of a material, its ratio with weight. In other words, modulo of elasticity to its density, which is called specific stiffness. So the combination of all these properties, as I said, we call them manufacturing properties. Let's look at a few examples together. Let's say somebody asks you to pick a right material for coin. Well, you say that's easy, coin. It's not a complicated thing, right? But what should we consider? Well, the appearance. Nobody likes a black coin, or maybe some does. The color, the weight. We don't want it to be very light or very, very heavy. And the ringing sound. Maybe some people care about the ringing sound when they strike a coin and flip a coin. They want that ringing sound. And also the feeling when you get it. You want to feel that you have these precious things, right? I'm just joking. Now, $2 and $1 probably is not that much of money. So what about corrosion? Well, imagine money circulate between many, many people, and human sweat is very corrosive. So you have to consider that one as well. How do you want to make a coin? Probably in one of those videos before, you watch how coins are made, and usually it is by cutting and then forging. So if this is the process, you need to pick a material that is forgeable. You can compress it to the shape and form that you want. And you consider all of these, and then you see other people's who are selling vending machine. They say, hey, you cannot pick any material because my vending machine is not like if you pick, for example, plastic, my vending machine is not going to work properly, and people are going to use fake coin. So a vending machine, basically when you put a coin there, it measures its geometry, like the size of the coin, diameter and thickness, and also it measures the electrical properties. For example, its resistance. So you need to then pick a metal, not a plastic, so they can measure its electrical property and so on. Health concern. Well, in the past, for example, in Europe, the coin used to have nickel in it, and it took a long time until people find out that some people are really and seriously allergic to nickel, and they decided to remove nickel from coin. Something very minor, but caused a lot of problem for many people. And again, it took a long time until people figured it out. And also the cost. So far you may say, well, I'm going to go with gold. Gold is the best, and it satisfies all of these criteria, but it's going to be very, very expensive, right? So maybe again, 1,000 years ago, gold would have been a good option, not today. So that's why people switch to an alloy, which is a combination of aluminum plus zinc plus tin plus copper. But you can Google the combination and the percentage of each of these materials. And that's a successful candidate for coin. Let's go to example 2. What material we should pick for a refrigerator door liners? By liners, I mean this area where you put the small items. And this is not my fridge. I don't have that much of healthy stuff. Mine is filled with other things. So what we expect from these liners? Well, to withstand the impact. Why? Because you may be angry and slam the door, so you want those, like the material, to stand the impact. Scratching and wear, of course, you put a lot of things in there and remove them constantly and put them back again. So it's going to be scratch and wear, and many other things. So, for example, the reaction with food. You don't want something that cause or get damaged or corroded under certain food. Of course, the appearance is important for you, and the way that you want to manufacture and assemble it, which later we'll see how these liners being made, and compatibility with other things, and also the cost. You don't want to pick a material that is very expensive. So a good candidate for this one, after considering all of these, would be polystyrene, which is a kind of plastic, which shortly we'll discuss it. And people in the past used to have this one until they find out that it reacts to vegetable oil. Reacts to vegetable oil. And if there is a slight vegetable oil, it's going to crack. So that's why nowadays people are going to use, people use ABS, which again, shortly we'll discuss it. That's a different type of plastic. And ABS is a successful candidate for this certain application. Moving on, a gun barrels. What material we should pick for that? So far, people were happy with HSS, which is high-speed steel, which again, we will discuss it soon, and its property. But then, over time, with the advance in materials, people wanted more. And what basically we are looking after when we pick a material for a gun barrel, of course, we want it to be very tough, so it doesn't crack under impact, and also we want it to have a high strength. And at the same time, the thermal conductivity and its thermal property is important for us. Wear resistant is obvious. The bullet is moving with a very fast speed. We don't want it to be very heavy. And also, we know that inside the barrel is rifled, which there are a spiral groove there to provide a spinning for the bullet and also a stability, or a gyroscopic stability for the bullet. So we want something to be able to also maybe machine it, or whatever manufacturing method we pick, we want to be able to do that as well. Well, again, as I said, maybe steel is a good candidate, but some difficulty, and it's going to be expensive to machine those groove there. Maybe a better candidate, again with advance in material, is something which we call it zirconia, which is a oxide of zircon, and it's a type of ceramic. So it's not a plastic, it's not a metal, it's a ceramic, which again we will discuss it shortly as well. And it satisfies all of these criteria that we want. So next time, if you plan to buy a gun, well, check to see what is the material. If it is ceramic, then go for that one, even if you pay higher money. Well, I hope nobody needs to buy a gun. Well, now that we have a gun, maybe if we decide to go to a war with somebody, we need to protect ourselves. Now we have a question that what should be a good material for a body armor? So let's see what we really need. So the main function of body armor, of course, is to protect us against bullet and shrapnel, right? But can I go with metal? Yes, that's a good candidate. metal can protect us against bullet. However, if we were like in 2000 years ago, that would have been okay for a, let's say, a soldier to wear a metal armor. But metal is very, very heavy, right? So what about plastic? Well, plastic definitely cannot withstand the impact and also the force by a bullet. So then we want something at the same time to be wearable, something which is soft and light. So if neither plastic or metal or ceramic works for this application, then what should we do? Here we rely on combination of material, and we invent something which we call it a composite material. And a composite material basically is made out of two things, one portion which we call it fiber, and another part which we call it a matrix. Let's say if I look at a certain point of this cloth under microscope, then I may see, let's say, something like this. Let's say I'm just looking at one small element. Inside that element, I will see a lot of fibers, maybe going vertically or horizontally. And they are all inside. So this is something which we call it fiber. And they are all inside of a softer material, which we call it matrix, which it holds everything. So the fiber usually is a metal. So it can be a metal or a ceramic. And the matrix, it can be a plastic. And it provides the function that we want for this particular application, which again, shortly you will see, we'll discuss the type of composite that we can use for certain application. And eventually my last example, let's say we want to cut a piece of wood and we have a circular saw. But the type of saw that I'm talking here is the industrial saw, a very large, like 30 or 40 inches diameter saw. And the saws that run at a very high speed, the speed of something around maybe 5,000 RPM or higher. So if we use this sort of saws, then to prevent vibration or lateral motion, we usually use on the side of a saw a pair of guides, basically. So a pair of guides at each side of the saw to protect the saw from lateral vibration or motion and make the saw stable. If we look inside this guide at each side, we'll see like a pair of pads. Here on this image below, this is something which we will call it a guide pad. So the image that I show, I just show the portion of the saw, and I show the saw on the other side. I move it so you can see from this picture what do I mean by the pad. So this pad, again, is at the two sides of the saw, and it has a main function of being like a bearing for this saw, right? It's a bearing. So what do we want from this part or the property of the material to pick for this application? Well, first of all, we want it to have a very good heat conductivity. We don't want it to hold heat. Otherwise, the saw is going to get hot and it's going to dish and damage and cause a lot of problem for us. And also, we want this material to be softer than steel, because steel is going to be in contact with this material. So the saw is made out of steel, right? So this is saw made out of high-speed steel, and it's a very hard material. So you can imagine if we, for this bearing, we use a very hard material, then if due to vibration, our saw is going to get damaged. So we want something softer than steel. Also, we want it to have low friction and So it is important for us. And the way that we decide to manufacture it, let's say, is by casting. So we want it to have a low melting point. Otherwise, again, it's going to be very expensive for us. And also the thermal expansion, we want it to be low. I have done tests with material that the thermal expansion is large. I will show you later, not today, but in future lectures, so that what happens if you use for this application with material that has a high thermal expansion. And also we want it to be inexpensive because these things are wearable, and you want with a cheap material because in a, let's say an average sawmill every day, let's say in 8 hours, for each saw, at least 3 times they change the guide paths. So you want something to be cheap as well. So it happened that none of the material or metals that we know can satisfy this, all these conditions until a guy, his name is Isaac Babbitt. I guess he died, yeah, probably, or maybe very old, like about 40 or 45 years ago. He invented something and he kept it as a secret. It still is a secret, and the material is called Babbitt. If you Google it, in Google it says, in Wikipedia it says the recipe is a secret, but people, of course, discovered the main materials, which the main materials are aluminum, copper, I believe lead, tin, and many other things which you can again look them up. As a matter of fact, I have one here with me. Let's see if I can quickly show you. So you guys, hope you can see my screen and at least my hand. So here I have a piece of broken saw with me. So the saw is made out of steel. We'll discuss it later. And also the tip of the saw, which is made out of carbide, which again, we'll discuss those later. But today we want to focus on more on this material, like this white material, which is the guide path, and it's a Babbitt material. And Babbitt, again, is an alloy of many components, which you can study it later. And later we will see when we discuss the topic of casting, we'll return back to this one as well. All right, so from this example, you see, it depends on application, we have to deal with variety of requirements, in fact, to make sure that we can satisfy all of those. And that's all to emphasize the importance of having a basic understanding of material before we start designing and manufacturing something. So it brings us to the objective that we have for this module. So as I said, we're not going to spend a lot of time on material. It's not the main topics of this course, but at least one lecture to cover the foundation. But during the lecture, we will see, we'll come back and review some of these things. So we will do a quick review of 4 types of material: polymers, metals, polymers, ceramic, and the composite structures. We basically look at their mechanical, physical, and chemical properties for these 4 types. And also some application, again, as a reference for you, maybe either in your capstone project, in other courses, or in future when you decide to manufacture something. But again, we're not going to go to in-depth analysis. If you want in-depth study of material, we have courses such as MEC 329, the same number as 392. Interesting, I just noticed that. It analyzes the mechanical properties of a material in depth. If you want to know more, then the manufacturing 378 is a course in manufacturing program. You know, it's a new program. This is a course. It teaches you a lot of things about material with focus in manufacturing. And of course, we have numerous courses in material from basic course to advanced course in ceramics and nanomaterials and coating and many things which you can take those courses. All right. So with that in mind, let's quickly review like this basically topic. So again, 4 categories of material, and remember, we're not going to talk about the natural materials such as wood or leather or wool or other things. No, we were talking about engineering materials. So engineering material, I can categorize them to basically 4 categories. So let's say to be organized, put a box around it, and let's say we want to have 4 categories. 1, 2, 3, and this is 4. So the first category is metals, second category is polymers or plastic, and third one ceramics, and then the last one composite. So plural, composites. All right. So basically 4 categories. Again, metals, polymers, ceramics, and then composite. So for metals, we categorize them to 2 main categories, 1 and 2. So the first one, we call it ferrous, and the second one, non-ferrous material. So again, many of these topics is very simple for you, or you have seen them in many other courses. It's just, bear with me, it's just going to be a quick review. So ferrous material, so the main one, iron and steel. And non-ferrous material, aluminum, copper, titanium, tungsten, and many other non-ferrous material. Polymer, we categorize polymer to 3 main categories. The first category, we call them thermoplastic. Second one, thermoset. And the last is elastomers. So thermoplastics are the material that if you melt them, if you make something out of them, then you can remelt it. If you heat it again, you can melt it again. Example of this one can be, for example, ABS. Thermoset, when you melt them and you shape them to the form that you want, you cannot remelt them. Example of this one can be epoxy. For example, the handle of the lid for the cooking pot in your kitchen, most likely it's made out of thermoset. It's a hard material and you cannot remelt it. But a piece of ABS, if you put it under fire, it's gonna melt. And elastomer, a good example is rubber. For example, the tire is made out of elastomer. So 3 categories, and again, shortly we'll see the structure of these things. Ceramics, again, we can break them to different categories. These categories...
sorry, can I interrupt for a sec?
Yes, please go ahead.
What is the difference between elastomers and the other 2 exactly?
All right. So I'm gonna get to that point, but
Okay.
yeah, I'm gonna get to that point. But in briefly, elastomers, they are very flexible. Thermosets, they are not basically flexible. But why they are like that, behaving like that, we'll get to that point shortly. So ceramics, so we can break them down to glasses. We can break them to carbides, graphites, oxides, which this one by itself has two categories, zirconia and alumina. So, and few others, which shortly we'll see that one as well. And then composite material. So composite material, as I said, is a combination of a fiber and a matrix. So, and it can be any of these three things, metals, polymers, and ceramics, but we're gonna have three main categories. The first category is something that the matrix is metal, so we call it a metal matrix. Second one is a polymer matrix. And the last one is a ceramic matrix. So the matrix is one of these three categories, but the fiber can be anything. So it can be metals, it can be rarely polymer, but it can be polymer or ceramic as well. So this is the main picture or the main category of the materials we should have in mind. So as I said at the beginning, when we talk about the manufacturing properties of materials, we are looking at four basically properties. The first one is mechanical. And as I said before, the mechanical, we talk about strength, the stiffness, toughness, hardness. So this one is not going to rhyme. Grip and fatigue. How many? 1, 2, 3, 4, 5, 6. So 6 basically things. So again, all of you are familiar with most of these. When we do a tensile test, we get a graph of stress and a strain. So if it is, let's say, stress, and this is a strain, and if we do a tensile test, we get a graph which looks like more or less something like that. So it has a linear part. This linear part, which we call it elastic part. So maybe I can do a better job and draw the first portion like a linear line, and then it gets to a curve, something like that. So on this graph over here, we call it SY, or the yielding strength of the material. And the slope of this line, let's say if the angle is alpha, the slope of this line, we call it modulo of elasticity. So we will conduct basically a tensile test, and from this tensile test, we can calculate SY and call it strength. We can calculate modulo of elasticity. So for toughness, basically what people do is they make like from the material, they make a more like a disc shape, and then this disc shape is going to be under pressure between two plates, something like that. Let's say you have the first plate here, and then you're going to have the second plate, and then we apply load here until it cracks. And based on these numbers, people can measure toughness, like how tough a material is before it cracks, and it has a unit of energy, like joule per area, something like that, which you can look for different material, look it up. So speaking of hardness, again, the resistance to penetration or indentation. So something that if you scratch on the surface of material, it's gonna withstand that. Again, you have seen probably tests to measure hardness. Two important tests. One is Brinell, a hardness test, and another one is Rockwell. If you forget these terminology and these tests, please look them up. It's very easy. So basically in Brinell test, people use like a sphere, and they like a tool, which is more like the head, has more like a spherical shape, and apply load on a surface, and they measure the indentation. While in a Rockwell test, it's more like a diamond shape. And again, people apply the load and they measure the indentation to measure the hardness of the material. What is creep? Creep basically is measurement of strain or displacement as a function of time. So if I plot a graph which on x-axis I have strain like epsilon, on x-axis is going to be time. So basically our goal here is to see over time how much the material is going to creep. And it's going to be a graph like that until it rupture and it's going to break at some point. So at the beginning, when time is 0, when we apply the initial load, of course, it's going to have some deformation. Over time, it slowly becomes weaker and deforms larger. Well, and eventually fatigue. Probably most of you took 325. You are familiar with the SN curve or stress and cycle curve. We put a material under cyclic load, and if you can hear a screaming noise, it's not my kid. I don't have kid. It's just the neighbor's kid. I'm not sure if my microphone picks that noise, but now they are quiet. Anyway, so sorry about that. So and the test, what people do is put a material under cyclic load. The x-axis is the number of cycle, and the y-axis is stress. So first we put a material under a very large stress and measure how many times we can apply the load before it breaks. And we keep doing it and until we get a graph which is more like this graph, and which is called the SN graph. And from this graph, people can measure basically something which we call it endurance limit. Endurance limit. For some material, maybe this number, such as the steel, is like 10 to the power of 6. And let's say at 10 to the power of 6, it gets to that flat line. So we are sure up to this certain stress or sigma F, sigma fatigue, the material can handle basically the stress that we want. And again, if you forget this concept, please go back and just read maybe a quick YouTube or a Google. You can refresh your memory. Physical properties, again, density, which usually we show it by rho. Density is important for us. The electrical property, the thermal property. These are all important things for us. When we talk about chemical property, basically the resistance of a material to corrosion, and is it possible to modify a material? So we call it property modification, or simply we say heat treatment. And the heat treatment process, again, two main categories of heat treatment. They are called annealing and quenching. Which in a simple word, annealing means heating up a metal to a certain degree before its melting point. And quenching means to put the hot metal into either water or salt water or oil, or maybe other chemicals, and depends on this chemical, we will get different hardness and different surface property. So I sent some video links to watch before this lecture, and I will do for the rest of lectures as well. So when I'm teaching something, I assume that you watch those videos, and in one of those videos, it explains how this process, annealing and quenching, can be done. So these are the manufacturing properties for different materials that we want to look at. So far it was all an introduction. So from what I can see, I expected we need another lecture to cover the rest. And the rest, we're going to look at the structure of metals, structure of polymers, the structure of ceramics, and also the composite and their application. So the next lecture, in fact, is more important because so far, as I said, are things that you most likely you already knew, and it was just an introduction. All right, so let me stop sharing my screen here. All right, see you guys later. See you on Thursday. Have a good evening.